So tokenization, these are the learning objectives. It was a really long chapter because the concept itself was pretty simple, but this book actually goes in more depth on how we go about tokenizing compared to tidy text. So it's pretty interesting. So we're going to look at what tokens are, define what different types of tokens there are, and the limitations of it maybe, and then building your own tokenizers using regex. So this sentence sums it up pretty good, I think. In tokenization, we take an input text and break it up into pieces of meaningful sizes. So we refer to these pieces of text as tokens and the meaningful sizes as token types. So for example, in this image here, the text, the cat sat on the mat, we break them down using words, right? So any white space is kind of separated. And this is the most common type of tokenization. But this isn't always perfect. So for example, in some languages, there are no white spaces, so like Chinese. I think this means she's my best friend in Mandarin. And as you can see, if you were to apply the white space tokenization approach, it wouldn't work here. And in certain Latin languages, there are pronouns and negation words that come before or after certain words, and they kind of become like one word, like this sentence, I don't like chocolate, but you have the little negation here with the N. So you have to make a call if you want to separate that or not. And similar things in English, so contraction of two different words, like would've, didn't, can't, and so on. So, define tokenizing using just word because it's the most common approach may not be the sensible approach if you're not careful. But that being said, let's do exactly that. And they use this package called HC Anderson R, which is a bunch of text. And they use this, the fear tree book example. Looks like this. And if we were to use a string R package, string split on this regex, so first, sorry, that's not lower alphabet, upper alphabet, and the the numeric, and there has to be one or more. So you can see it's split on pretty much white space, far down in the forest, blah, blah, blah. But this actually omits the main hero's name, Fear Tree, with the dash in the middle, because it wasn't specified in one of the regexes. So right from the get-go, you can see kind of it's a complex problem tokenization is, but you actually don't have to write any custom regexes yourself because we have packages like Tokenizers. So yeah, exactly the same thing. I know this split the fear tree in here too, but there are a bunch of, sophisticated rules they follow on a universal standard, I think. Yeah, there's a bunch of them. I didn't really understand everything, but it kind of makes sense, right? Break at the start and end of text unless the text is empty, and so on. So that's what tokenization is in the nutshell. So yeah, different types of tokens. This book covers quite a bit. We already looked at the words, which I'll cover as like an intro, but they also cover characters, sentences, lines, paragraphs, and most importantly, engrams. So yeah, tokenized based on words, tokenized words. As expected, we're going to see far down in the forest. And we can actually use honest tokens in tidy text, which does the same thing, but it gives you a different data structure. But under the hood, this is honest tokens in tidy text. Let me go to my RStudio. Just want to show you this super quick. Okay. So if I run this, so sample table is this here. Yeah, 2 rows with a bunch of text. And if I debug this, so see that token func here? This is where the magic happens. And I'll dive into this find function internal. Shit. Function. So what they do is basically they look at tokens that are passed into the unnest tokens function, as well as format. And I believe, no, I think that's it. Okay. And then they pretty much paste it into a, where is it? See that page 0 tokenized tokens. So what that does is this actually gives you tokenized words from the Tokenizers package. So it's basically under the hood, it's exactly the same thing. And the only time they use a different engine is when your format is not a text. So I think it can be HTML. What else is there? Yeah, so text, man, latex, HTML, XML, and only when it's text, it uses the Tokenizers package. So we'll keep going on this if else loop. So TF. So use methods tokenize words. So token func is can't see it. On this. Yeah, so that's how unnest tokens works. If you didn't know before, I thought that was pretty cool. Slides here. Yeah, so under the hood, it's exactly the same thing. You can use tokens characters, and it'll paste a nest and characters together and find that function in the tokenizers package. What else do we have here? Yeah, so you can pass in a bunch of tokenized words arguments through unnest tokens, because in the source code, they don't use this ... anywhere else. So this is only used in the, I guess you can see it here. But yeah, it doesn't pass through the other engine that I was talking about. They just use it on tokenized words in the tokenizers package. What else? There's this argument, which is pretty cool. It strips out all the, dots and punctuations. And if it's false, it's going to preserve the dash that we were looking for. Okay, so character, so each letter, right? So your token type is a letter, and you can pass in the same arguments, like strip, lowercase is true, blah, blah, blah. And it's essentially this regex right here. Punctuation, I don't know what you call that, but syntax, punc syntax and white space syntax. And they, after stripping those, they feed it into the word boundaries methods that we were talking about earlier. So same sentence, but it gives you a bunch of different letters. Same thing in unnest tokens. So you can pass in as characters, and it's going to give you FARD, blah, blah, blah. Okay, so ligatures. This is when you have to be really careful when tokenizing based on letters, because certain letters in non-English especially are combined into words. So when multiple letters are combined into a single letter, that's called ligatures. And it oftentimes happens with an F. So FI becomes this and FL becomes this. And I did a quick Wikipedia search, and they said it's literally because it doesn't look pretty, and it collides in like your typewriter or like a print setting back in the days, so that they literally just made it one single letter. So there's 2 types you got to watch out for. Is it a stylistic one or a functional one? And is it actually meaningful to capture, the 2 letters in the ligatures? One of the examples they covered in the book is the S set in German. So if I were to tokenize character this, it doesn't know the difference between the S and the Z. But this may not be what you want if you're a Swiss person, because they actually don't do this whole SZ deal and they just do SS. I thought this was pretty funny. In Wikipedia, they made a joke. Apparently, because Swiss don't use the SS, I'm not going to try and pronounce this, but in Massen means in mass. But if you were to use the SS, it's in moderation. I don't know, I thought it was pretty funny. Word, we already covered this, but you can use a bunch of dplyr functions to do cool, summarizations and group bys. So here we're covering 2 different books and counting the frequency of the tokens that are most common. So you see a bunch of stop words, right? The, and, it, a, and so on. Okay, engrams. Engrams are a continuous sequence of n items, whether that's syllables, letters, words, what have you. This is a unigram using the word tokens. Hello, my, hello, they, my little. Bigram is 2 words, fear tree, fresh air, and trigram. What's good about engrams is you can capture more meaningful words that are otherwise lost if you were to use a unigram. So for example, fear tree the meaning was lost because we separated the 2 words into their own tokens. It does so by sliding across a given text and creating overlapping sets of tokens of size n. You can use the tokenized engrams in the tokenizers package, as well as the NIST tokens. Same deal, but I thought this was pretty cool. The n and min argument, which actually I'll come back to this, which gives you a bunch of different engrams at the same time. So we said go up to 2, but give me at least 1 engrams. So we're seeing far, far down, down, down in. So it's giving you a unigram and a bigram at the same time in the same operation. Now, coming back to this, this is pretty obvious, right? Each dot is a story in the package, the Anderson package. And as we're using more n, so quadrigram, there's not a whole lot of, what do you call it? Frequent engrams that kind of pop up at the same time, because the tokens are so big that they're so unique. But if we were to use one unigram, there are a lot of overlapping words that are used multiple times, but you don't have as many different unique tokens. Okay, this was a little confusing. Line, sentences, and paragraphs. They covered this in tidy text, I think, with the Jane Austenar package. They pretty much take a bunch of text, add the chapters in the beginning of the sentences, and collapse them, so make them into like a giant single text, and then chop them again into chapters, paragraphs, and sentences. So that's basically the idea with these 3 token types. You take a bunch of text, make them into a single giant string, and then split them again however you like it. Should I cover this? Yeah, so this collapse call is doing a bunch of the work here. Should I cover this? Do you guys want to do this in our studio? I can kind of show how this works if you want. Okay.
This is the chopping into sentences?
Yeah.
Okay. Yeah, I was in the tidy text mining.
So that's the story from Jane Austenar. A bunch of sentences that are up to 80 words, I think. And what they do is full text like so, and then they collapse it into a single giant string using the, the new line character delimiter. And then they tokenize on paragraphs, which I think just cuts it in the new line character and just gives you a nice list of words, list of text. And then you unlisted, make it into a tibble. And then, so now you have a row per paragraph. And since we have a row per paragraph, we can number the rows into the paragraph number. So I'll just return it. And we get this per chapter, per paragraph into a row. That's in essence what it's doing. Same idea in the sentences. We're taking the fear tree, make it into a giant string using a space. And then since we can use a space as the delimiter, we can just tokenize them. Okay, all right. So this is when tokenization breaks down in sentences like this. Don't forget you owe the bank $1 million for the house. So tokenization is a crucial step for any kind of text analysis. Defaults work well for the most part, but we have to be careful. So the book pointed out two different words. So don't, is it a one word or should we split it into two, do and ent? This again is a, I think the next chapter covers it with the stop words. And the same thing with the $1 and the punctuation at the end of the sentence. Should we strip out the punctuation? If so, we actually are not able to, if there was another sentence there, we wouldn't be able to tokenize it into a sentence. And the $, should we keep the $sign? Should we do a $1 as one token and so on? So context matters. You may not care too much if you're just interested in seeing what kind of words pop up in sentences. So for example, Twitter is a good example. Maybe you're doing like a sentiment analysis and you're just interested in what kind of words are people using and are they good or bad? That type of sentence, that type of context doesn't really matter if you're careful. Yeah, I shouldn't say that, but you know, you don't have to be as careful with these subtle rules. But if you're doing like a grouping or, you know, what's the example they use? Yeah, social grouping analysis. You might want to capture everything because you're interested in the style of languages certain people are using. And a good example is deliberate capitalization, multiple white spaces, and overuse of the exclamation mark. That's what the book listed as examples. Yeah, so using a small number of tokens may be fast, but you may lose some meanings. You may not have as much of a vocabulary list, whereas if you're using like a unigram, you may be able to match every single one of those, but you may lose certain meanings behind like a bigram, for example. Okay, so this is the last thing I wanted to cover, building your own tokenizers using regex. There's two main approaches: splitting the text up according to some rule and making tokens out of them, or extracting the tokens. So a subtle difference, but it'll become clear once we go through some examples. What did I do? I think I did 3 examples from the book. Mimicking tokenized characters. Basically this regex, right? Like you string extract. So you're extracting any alpha character 1 or more times. But now it doesn't really matter if you use this, what do you call it? quantifier or not in this case, but it's good to have it in there. So we're going through the sentence and picking out all the alpha characters in this sentence. So the space is omitted because it's not an alpha character. Yeah, and here's a Danish sentence, and they won't pick out this word, this letter, and this letter because it's not an alphabet. So, or sorry, if you were to do this, so AZ to AZ, like an English alphabet, it won't pick out other letters in other different languages. But in this, what do you call it? In this syntax, it picks up. Exactly, yeah. Yep. And then the second example is allowing for hyphenated words in tokenized words. So like the fear tree thing. So the first approach we're going to try is by splitting the sentences on white space. So this is a pretty good solution because it actually captures everything. It's only picking out on white space, so it doesn't care if there's a hyphen or alphabet or an apostrophe. So that worked pretty good. What else did it do? And we removed, what is this? Okay, so we did this, and then we're mapping through this list, and then we're removing the first punctuation or more. Oh yeah, so we're removing punctuations. So any punctuations that come in the beginning of a word or at the end of a word, and there has to be one or more. So we're losing this fear tree dot, so we're losing that dot there. So that was pretty simple, but it gets a little more complicated with the extract method. So say we want to pick out some kind of alphanumeric word followed by a hyphen and followed by another set of alphanumeric characters. So it picks out fear tree fine, but it loses everything else because we didn't use the question mark quantifier. So this means 0 or more. So if we go like this, it's going to pick up everything. But we lost some details here. So we lost the apostrophe, we lost the punctuation. So we're gonna include this single quotation into the alphanumeric quantifier by doing this. So we're saying find anything that's an alphanumeric or a single quote, find it one or more times, followed by a hyphen, and another set of the same thing, but it's actually optional. So we get back our yeah.
This apostrophe, what does it do here?
It's picking up this here. So if you see here, it lost the apostrophe T. And by including this in our
I mean,
alpha
in this
class,
regis. So by including this in the alpha class, what does this mean? What is it doing here?
it picked up the apostrophe.
Okay.
So from here to here, we're literally just saying single apostrophe is an alpha class, if that makes sense. It isn't, but included in the search.
Okay.
So it doesn't, the regex doesn't stop here. Whereas here it stops here because it doesn't recognize the apostrophe. Does that make sense?
Yes. Yeah. I mean, I'm just going by. Okay, I will check it. I mean, the alpha, I know it does have these two like braces, right? But this one comes after the first braces, after the first square bracket. So what? Anyway, I will check what does that mean, because I'm really confused why they put this in the first square bracket, not the second one.
So why is it
what I mean?
Not here?
Yeah,
like
yeah,
this?
not the Yes, or not outside, not out, or outside of the second one.
Like here?
Outside of all the, yes.
Yeah, that's a good question. I don't know, because I don't know, maybe this is a class on its own, and then we're wrapping it into another set of square brackets with the target quantifier. Maybe that's it. Because here we don't use double square brackets. We're just using one.
Okay. Oh, okay. Yeah. Oh, yeah.
I think that's it. I'm not a regex guy, but I think that's it.
Mm-hmm.
Okay. So yeah, we picked up the apostrophe T, but finally we're missing this A because we have to pick up an alphanumeric hyphen and an alphanumeric. So the minimum number of characters that this regex looks for is 2. So what we can do is leave this alone, and then we can set up another one where we say if there is an alphanumeric of 1 or more, or sorry, of exactly 1, pick that up also. So it goes through the sentence. These pick up all the way up to here, and then it reaches the alphabet A, and then it fails here because it doesn't find the second alphanumeric, and it just goes to the next, or pick up just one alpha, which is letter A. And now we have the whole sentence, and we wrote a custom regex to mimic what a nest token does. So that was quite a bit. Any questions here? I'll just kind of stop for a second. Okay, take that as a no. Finally, they covered the character Engram tokenizers. Now, I don't know when they covered this, but they threw it in there in the book, so I'm going to cover it. So what they're doing with this is basically going through the sentence, tokenizing by characters, but at a given length. So they gave 3. So we're seeing far, the, hound, the, for, or, and they do it by string locate all. Are you guys familiar with this function? I wasn't, so I had to kind of dig in a little. So if you want me to show in our studio, I can.
I know it.
Okay. So yeah, that's what it did. It looked for a character. So where for this character? I'm going to say syntax. Character syntax. Exactly 3 times, and this is a positive look ahead, I think. So it locates the next time they find exactly 3 characters, and then they split based on the locations of the text. So it'll return like 4, 7, and so on, and then it's subbing the what's the Y again? Is that the map to X? So that's entire text. So they're subbing the text with the locations, and you know what? I'll do it. I'm confusing myself. Your tree. All right. Our X is the text, and where N is, okay, this is 3. I'll just debug is, it's colliding with the variable name. But if we print out the regex, word looks like this. So positive look ahead, word 3 times. And if we run this line, it gives you this. So what this is pretty much, I'll just cover the first one. It's going across the sentence and looking for the next time the word has shown up 3 times. So it goes start at 1, and the next time it finds it is at position 5. So 1, 2, 3, 4, 5, D. So it starts at 5. The next time it finds it is at 6, which is O, so OWN, and so on. And then we're using the map tool to let's just do this string sub. Is that gonna work? So yeah, it's using this starting sentence, 1, with 1 plus 3 minus 1. So what is it? 3. So it's subbing the 1 through 3 and returning that as a return value. Did I say that correctly? Did I say that's how string sub works?
Can you say that again?
Yeah, so it's using the position index the first time the 3 characters show up. So that's number 1 in the F. And then it's going 1 plus 3 minus 1. So it's going 3 more. Yeah, 3 more. 1, 2, 3. Sorry, 1, 2, 3. So it's capturing this and then returning this amount. How does it work here?
Okay, so let's see. STR locate all returns indices. And then it's using that list of indices in map 2, where you have the index, and then I can't see because it's highlighted.
Oh.
The STR sub. Oh, okay. It's passing map 2 to the function str sub, where the .y and the .x are going to be, it looks like the vectors in that list.
Yep.
And it's doing it's taking the first you have square bracket column 1. Okay. I'm trying to think why it's repeated. Oh, it's okay. It's x plus n minus 1. Okay.
So that's a 3-part, right? I think, like from position 1, go 3 more, and then truncate the whole sentence into that little sequence. That's what it's doing.
Yeah, I think so, because the function takes in x and n, and whatever you put in for n, it's going to go back 1 for the second substitution.
I think so, right? Let's just plug this in.
That's what it looks like.
Sub.
Yeah, because you have the submit for str sub, you have the
Yeah, that's what it's doing, I think.
Yeah. But if you don't take the white space, it will it may capture that as well.
This.
Let's see. 1, 2, 3. Well, yeah, no, that's right.
Yeah, so I think that's what it's doing. It's going through this index where they locate 3 consecutive letters, and then use that as a start point, and then go 3 more, and then yeah, substitute the entire sequence to that little sentence or little 3-letter sequence. I think that's what it's doing. Yeah, so where is it? So that's what it's doing. And then if you were to do 4, it'll go fired, you know, and so on.
Yeah. Okay.
So yeah, that's what character engram is doing, what they're trying to say. Now, I didn't find this in the book.
It's
they
just
say,
subsetting. But yeah, okay. Got it.
Yeah, I think so. So they say, let's next turn our character engram tokenizers into a function. But this is my first time seeing this in this chapter. So I don't know, maybe they forgot or I didn't see it anywhere. Okay. And the rest of the chapters are pretty simple. I didn't, oh no. They were relatively short, so I didn't make it into a slide. So there are tokenizers for different languages. I didn't try this personally, but it's a lot more complicated because unlike Latin languages, you can't use white space to tokenize stuff. But there are packages. I haven't used them myself. And then you can use the benchmark function to compare different tokenizing functions. So they did corpus, tokenizers, text to vec, BaseR. I only use tokenizers to be completely honest. And you can see it's pretty fast compared to especially BaseR, where string split is not necessarily meant to be used as a tokenizer. So do use specific packages made for this purpose. What else? Yeah, so I think that's everything. Tokenizing is the very first step that you need to do when you're trying to do a text analysis. And there are a bunch of different ways to do it. And do use care because you may get some unexpected results if you're not careful, especially with regexes and engrams. And yeah, that's it.
Right. Thanks. Sorry?
Oh, here it is. No, sorry, I lost my stuff here, bar. Okay.
Yeah. So I think this is pretty good chapter. And one thing I know, like you can do also that is SMLTAR, which may be because I see the benchmark here. They don't, I think they don't include SMLTAR. And SMLTAR is one of the widely used Python package, but the SMLTAR also may, I think, may beat one of these guys. I don't know if because from Contida guys, so it is also used for tokenizing. Yeah. I don't know if Laila, have you tried before?
Not in R, but I just recently had to use it in Python. So I might check it out, but you said that there is an R version of SMLTAR.
Yeah, so I think in Python, I think SMLTAR is one of the widely used, and
yeah,
this wrapper.
It's like the, it's like the package for like this basic NLP task.
Yeah, yep. Yeah, so maybe I would try to run the the benchmark with the SMLTAR also and see what happens. Yeah.
Yeah, do it and let me know.
All right. So I think we are good. And next week I think is stop words, and I will take that chapter and present the step words. And week after is going to be Johnston, where he will go through the stemming chapter.